What would happen if all the continents formed a single territory? What if I told you that this reality already existed millions of years ago? Dear traveler, welcome back. Today we're going back in time to 300 million years ago, when our planet looked radically different. A single supercontinent ruled the Earth, Pangea. This colossal landmass, surrounded by an immense ocean called Panthalassa, brought all the land masses together in a single block. Scorching deserts stretched as far as the eye could see in its center, while its coasts were home to an abundance of life, populated by creatures now extinct. A world where you could have walked across what would later become America, Africa, Europe, and Asia. But before you set off on your next adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! German meteorologist Alfred Wegener is recognized as the pioneer of the theory of continental drift. In his 1912 book, The Origin of Continents, he was the first to propose the idea that today's continents were once united into one large landmass. This bold approach marked a turning point in our understanding of terrestrial geology. Wegener suggested that before they began to fragment and drift toward their present positions, the continents formed an immense supercontinent, which he called Pangea. This idea broadened our view of geological dynamics, suggesting that there had been a period when all the continents were united, creating a unique environment conducive to specific ecological interactions. In 1912, Wegener refined his concept by naming this ancient supercontinent the Carboniferous Pangea, referring to the geological period in which it would have existed, during which climatic, geological, and biological conditions were radically different from those of today. According to Wegener, Pangea was a vast landmass encompassing lands now scattered across several continents, paving the way for further research into the configuration of the Earth through the ages. Wegener put forward several convincing pieces of evidence to support his theory of continental drift and the existence of Pangea. Firstly, the arrangement of the continents resembles pieces of a giant jigsaw puzzle, a striking observation he made in the early 20th century. For example, the northwest coasts of Africa and eastern South America seem to fit together, suggesting that they were part of a single continental mass. Another key argument is the distribution of fossils. Identical fossils of ancient species, both terrestrial and aquatic, have been found on continents now separated by vast oceans. For example, similar freshwater reptile fossils have been found in Africa and South America. Given the impossibility of these creatures crossing the Atlantic Ocean, their presence on two separate continents clearly indicates that they must once have been connected. What's more, rock strata patterns reinforce the idea of Pangea. Geologists have noted similar rock formations on distant continents, confirming that these rocks developed together before separating. The similarities in rock layers and coastal patterns caught the attention of scientists, who realized that these formations could not be the result of chance. The global distribution of coal also adds weight to the argument for Pangea. Coal generally forms in warm, humid environments, which makes its presence into the Antarctic ice caps, where conditions are currently cold and dry, surprising. This suggests that Antarctica was once located in a milder location, favorable to the formation of vast coal reserves. In November 1926, at a symposium organized by the American Association of Petroleum Geologists, the term Pangea was introduced into the scientific literature, marking an important step in the recognition of Wegener's ideas. Initially, Wegener maintained that the fragmentation of Pangea was due to centripetal forces resulting from the Earth's rotation. Despite his innovative ideas, Wegener met with resistance, as he could not satisfactorily explain the mechanism of continental drift. His hypothesis proved physically unrealistic and unable to explain the complexity of continental movements. It was only after his death, with new data, that his ideas began to gain widespread acceptance. In the 1960s, English geologist Arthur Holmes proposed an alternative mechanism based on convection in the Earth's mantle, suggesting that the convection currents could drive the movement of tectonic plates. At the same time, research on the ocean floor revealed features essential to understanding the expansion of the seabed. These discoveries led to the theory of plate tectonics, largely replacing earlier ideas of continental drift. This new theory not only explained the existence of Pangea, but also described how continents move slowly over time, leading to their current fragmentation. Pangea formed around 335 million years ago, unifying almost all the planet's landmasses into a single supercontinent. However, Pangea is not the only supercontinent the Earth has known, but it is the most recent of all. The formation and fragmentation of supercontinents seems to follow a repetitive cycle throughout Earth's history, and it is likely that other supercontinents existed before Pangea. Pangea is not the first supercontinent that scientists have assumed existed. Thanks to geological evidence, several supercontinents predating Pangea have been reconstructed. These include Pannotia, which is thought to have formed around 600 million years ago at the end of the Precambrian, before breaking up again around 50 million years later. This supercontinent would have played a key role in the geological upheavals of the time, notably by modifying oceanic and climatic currents. Another hypothetical supercontinent is Rodinia. It is thought to have originated around 1.1 billion years ago during the Proterozoic era. Its formation is essential to the Earth's geological history, as Rodinia would have been the origin of future continents and supercontinents. After existing for around 350 million years, Rodinia split around 750 million years ago, triggering major tectonic and climatic upheavals, such as the snowball Earth hypothesis, where the planet would have undergone near complete glaciation. Geological evidence also suggests the existence of Columbia, a supercontinent that would have existed between 1.8 and 1.5 billion years ago. Columbia is still largely unknown, but its existence raises questions about the cycles of supercontinents that have marked the tectonic evolution of the planet. Going even further back in time, scientists have identified tentative evidence of a supercontinent called Kennerland, which would have existed between 2.7 and 2.1 billion years ago. Kennerland, like its successors, played a crucial role in the early stages of the Earth's tectonic evolution, and its disintegration probably contributed to major climatic and atmospheric changes. The oldest theoretical supercontinent is Valbara, whose existence dates back some 3.6 to 2.5 billion years, to a time when the first forms of the Earth's crust were beginning to stabilize. If Valbara really existed, it could be the starting point for the evolution of supercontinents on Earth, bearing witness to the early tectonic processes that shaped our planet. The supercontinent Gondwana played a key role in the formation of Pangea. Prior to the assembly of Pangea, Gondwana already existed, formed from the fusion of several large continental blocks, mainly located in the southern hemisphere. It included lands that today correspond to South America, Africa, Antarctica, Australia, and the Indian Peninsula. Gondwana land remained an important entity even after the disintegration of Pangea, separating into separate continents much later in geological history. The formation of Pangea itself is often explained by the convergence and collision of two great supercontinents, Gondwana and Laurasia. Laurasia consisted mainly of what is now North America, Europe, and part of Asia. Prior to the formation of Pangea, Laurasia was formed by the collision of the Siberian continent with Laurussia, also known as Euramerica, a minor supercontinent that already existed at that time. This tectonic collision took place during the Carboniferous period, some 350 million years ago. The creation of Pangea was not the result of a single short-lived event, but of a series of successive collisions between distinct continental blocks. Following the convergence of Gondwana and Laurasia, other smaller land masses such as Siberia, North China, and South China gradually joined this immense tectonic structure. The final formation of Pangea led to the emergence of a huge unified landmass that dominated the Earth's surface for around 160 million years. During this period, Pangea profoundly influenced global climate, ocean circulation, and the evolution of life on Earth. However, the tectonic forces that had led to its formation continued to act, and around 200 million years after its formation, Pangea began to fragment under the effect of plate tectonics. The process of disintegration led to the creation of the continents we know today. Gondwana land, one of the main components of this fragmented Pangea, continued to exist for several million years before splitting off in its turn, giving rise to today's southern continents. Prior to the formation of Pangea, several complex tectonic processes shaped the geography of the primitive continents. One of the key events was the movement of the minor supercontinent Proto-Laurasia away from Gondwana, across the Panthalassa Ocean, a vast expanse of water that dominated the northern hemisphere. The separation of these two great land masses led to the creation of a new ocean, the Proto-Tethys Ocean, marking the beginning of a series of geological changes that were to transform the Earth's surface. Shortly afterwards, Proto-Laurasia itself fragmented into several distinct continental blocks: Laurentia, corresponding today to North America, Siberia, which evolved as an independent continent, and Baltica, which would become the basis of Eastern Europe. This tectonic rupture not only gave birth to these continents, but also led to the formation of two new oceans, the Iapetus Ocean and the Cantae Ocean. While Laurentia remained to the west, Baltica was established to the east, and Siberia lay to the northeast of Laurentia. During the Cambrian era, Laurentia, which would later become North America, was positioned on the equator, bathed by three major oceans: the Panthalassa Ocean to the north and west, the Iapetus Ocean to the south, and the Cantae Ocean to the east. This geographic configuration favored exceptional marine biodiversity, with a proliferation of primitive marine life forms during the Cambrian explosion. But these conditions changed with the arrival of the Ordovician, a period during which a major new geological event took place. The microcontinent Avalonia, which would later form the northeastern United States, Nova Scotia, and part of England, broke away from Gondwana and began its drift towards Laurentia. The end of the Ordovician period marked a new stage in the formation of supercontinents. Baltica collided with Laurentia, followed shortly after by Avalonia, which merged with these two landmasses to form a minor supercontinent, Euramerica, also known as Laurussia. This process led to the closure of the Iapetus Ocean, while another ocean, the Rhec Ocean, developed along the southern coast of Avalonia. This tectonic collision not only brought several continents together, but also contributed to the formation of the Appalachian Mountains, which today lie in northeastern North America. During this period, Siberia lay close to Euramerica, separated by the Canty Ocean, another remnant of this period of tectonic fragmentation. Meanwhile, Gondwana, still unified, continued its slow drift towards the South Pole. This gradual movement of Gondwana represented the first step in the wider process of the formation of Pangea, which would be completed several million years later, creating a single supercontinent that dominated the Earth. The second stage in the formation of Pangea was marked by a series of complex tectonic collisions, the most important of which was the meeting of Gondwana and Euramerica. By Silurian times, the Baltic, a continental block corresponding to part of present-day Eastern Europe, had already collided with Laurentia, giving rise to Euramerica. This continental mass was the result of the fusion of Laurentia and Baltica, but Avalonia, a microcontinent to the northeast, had not yet fully joined this supercontinent in formation. The remnant of the Iapetus Ocean remained in the form of a narrowed seaway between Avalonia and Laurentia, testifying to the slow convergence of these two land masses. Meanwhile, other tectonic upheavals were taking place in the southern hemisphere. Southern Europe, still part of Gondwana, began to fragment and drift northwards. This continental fragment moved towards Euramerica through the newly formed Rhec Ocean, which separated the southern land masses from those of the north. During the Devonian, this small, largely submerged plate collided with the southern Baltic, further modifying the structure of the continents. At the same time, the Canty Ocean, a brother of the Iapetus Ocean, shrank as a Siberian island arc collided with the eastern Baltic. This collision contributed to the closure of this ocean, and behind the Siberian island arc, a new ocean began to emerge, the Ural Ocean. The latter formed as a result of the convergence of continental masses, paving the way for future tectonic collisions that would shape the region. At the same time, towards the end of the Silurian, two distinct continental blocks, North China and South China, broke away from Gondwana and began to drift northwards. Their movement took them across the slowly shrinking Proto-Tethys Ocean. To the south of this ocean basin, a new ocean, the Paleotethys Ocean, opened up, marking the appearance of another important element in the Earth's primitive geography. During the Devonian period, Gondwana itself began to move northwards, causing the progressive closure of the Rhec Ocean as it approached Euramerica. This convergence movement laid the foundations for the third and final stage in the formation of Pangea, which would unite almost all the planet's landmasses into a single massive supercontinent. These repeated collisions, this slow but constant continental drift, were to transform the face of the Earth, modifying ocean currents, climate, and the evolution of living species for millions of years. At the beginning of the Carboniferous, a major process of tectonic convergence intensified, shaping the configuration of continents and mountain ranges on the Earth's surface. Northwest Africa, part of the supercontinent Gondwana, came into contact with the southeast coast of Euramerica, a landmass that included Baltica, Laurentia, and Avalonia. This collision resulted in the formation of the Southern Appalachians, a mountain range that stretches from the north to the southeast of North America, as well as the Meseta Range in present-day Spain. Meanwhile, South America, another fragment of Gondwana land, was slowly drifting northwards, approaching the southern part of Euramerica. At the same time, the eastern parts of Gondwana, including India, Antarctica, and Australia, were moving towards the South Pole, triggering major climatic changes in these regions, including the formation of glaciers. During this period, North China and South China, which were separated from Gondwana, existed as independent continents, floating in the Proto-Tethys Ocean. For its part, the microcontinent of Kazakhstan began to shift and collide with Siberia in the Middle Carboniferous. Siberia itself, which had been an isolated continent since the disintegration of the supercontinent Pannotia, now saw its borders modified by this new collision. Towards the end of the Carboniferous, another major tectonic event took place: the collision of western Kazakhstan with the Baltic. This meeting closed the Ural Ocean and initiated the formation of the Ural Mountains, a mountain range that still marks the border between Europe and Asia today. The melting of these lands led to the formation of the supercontinent Laurasia, which was a major part of the Pangea that was still forming. Simultaneously, South America, still moving northwards, eventually collided with southern Laurentia, closing the Rheic Ocean, a remnant of the Silurian era. This collision completed the formation of the Southern Appalachians and also contributed to the creation of the Ouachita Mountains, a mountain range today located in the southern states of the USA. Meanwhile, Gondwana, located near the South Pole, saw the formation of glaciers on many of its lands. In Antarctica, India, Australia, Southern Africa, and South America. Towards the end of the Carboniferous, the North China Block collided with Siberia, marking the complete closure of the Proto-Tethys Ocean and ending one of the oldest ocean basins on Earth. This event also helped consolidate the landmass of Pangea. At the beginning of the Permian, another tectonic movement took place. The Cimmerian Plate, a landmass located south of Gondwana, broke away and began to drift northwards towards Laurasia. This drift led to the opening of the Tethys Ocean to the south of this plate, while causing the gradual closure of the Paleotethys Ocean. At this stage, most of the world's landmass was united in a single massive supercontinent, Pangea. During the Triassic period, Pangea rotated slightly to the southwest, further altering its overall orientation. During the same period, the Cimmerian Plate continued to cross the Paleotethys Ocean, which was gradually shrinking. This process continued until the Middle Jurassic, when the Paleotethys Ocean finally closed completely from west to east, leading to the formation of mountains through a process known as Cimmerian orogeny. This closure also shaped the boundaries between the continents as they formed. At its peak, Pangea had a shape resembling the letter C, with a vast inland ocean called the Tethys Ocean, framed by the lands of the supercontinent. This unique configuration, with an ocean at the heart of Pangea, profoundly influenced the planet's ocean currents, climate, and biodiversity before Pangea began to fragment, starting a new geological cycle that would lead to the formation of today's continents. Climatic conditions on Pangea were different from those we know today. At that time, the Earth was a radically different world from the one we live in today. In the early Permian period, the Earth alternated between cold glacial periods when large ice caps covered part of the surface, and warmer interglacial periods, when these glaciers melted. During glacial periods, water was trapped in the glaciers, causing sea levels to drop significantly, sometimes by more than 100 meters or 330 degrees Fahrenheit. However, greenhouse periods, i.e. without permanent ice at the poles, are characterized by higher temperatures and higher CO2 levels. Temperatures average 30 degrees Celsius or 86 degrees Fahrenheit, creating a warm, humid environment. The atmosphere was loaded with carbon dioxide, with CO2 concentrations 5 to 20 times higher than today, generating a considerable greenhouse effect. When glaciers melted during interglacial periods, sea levels rose, transforming coastal areas into shallow seas. In warm interglacial periods, coastal swamps thrived, populated by insects, amphibians, and reptiles, while shallow seas teemed with marine life, with creatures lining the seabed and others swimming in the warm waters. Climatic cycles alternating between glacial and interglacial periods led to significant variations in sea level. When glaciers advanced, the seas retreated, exposing more land. Conversely, during periods of warming, melting glaciers caused sea levels to rise, flooding coastal plains and forcing flora and fauna to migrate in response to changing conditions. Over time, the Earth's internal heat began to accumulate beneath the supercontinent Pangea. This heat caused the land to rise, forcing the shallow seas to recede. As a result, Pangea's climate became progressively hotter and drier, and immense equatorial deserts formed as water became scarcer. These new climatic conditions were marked by high temperatures, violent winds, and frequent dust storms. Instead of two desert belts separated by a humid tropical zone near the equator, as is the case today, Pangea comprised a vast desert region that extended into the equatorial zones. It was due to Pangea's large size, which disrupted normal atmospheric circulation. The great deserts of these periods were generally located in subtropical zones due to atmospheric circulation, notably Hadley cells, which create arid conditions in these regions. Scientists have discovered this by studying rocks and sediments from this period, including evaporites, which are salt deposits formed by the evaporation of water in arid environments. During the Permian and Triassic, these deposits show that the interior of Pangea was extremely dry, with hyper-arid deserts covering the equator. The study of a halite core from the Middle Permian Nippawalla group in western Kansas has provided valuable information. This research has led to a better understanding of the extreme climatic conditions that prevailed within the supercontinent Pangea. At the time, this region was an immense desert plain with temporary salt lakes that formed and evaporated, leaving behind salt deposits such as halite. This type of landscape resembles the salt lakes found today in southeastern Australia, notably around Lake Tyrrell. Brine inclusions trapped in the salt of these deposits reveal exceptionally high temperatures at the time, reaching up to 73 degrees Celsius or 163 degrees Fahrenheit. These values far exceed those observed today, even in very hot places like California's Death Valley. In more recent periods of the Nippawalla geological group, maximum temperatures were a little more moderate, around 43 degrees Celsius or 110 degrees Fahrenheit, but still very hot. Life in these regions was difficult, with very high temperatures during the day and freezing at night. These extreme climatic conditions were linked to the unique configuration of Pangea, where vast continental expanses lay far from the oceans. This situation led to very marked temperature variations between day and night. Another episode of intense heat occurred later in the Cretaceous, marked by deposits of marine evaporite such as tachyhydrite, indicating exceptionally warm climatic conditions. This shows that throughout Earth's history, certain periods have experienced climates far more extreme than those of today. Only the coastal areas of Pangea near the Panthalassa Ocean enjoyed a milder seasonality, alternating between a rainy and a dry season. This period culminated in a dramatic event, the Great Extinction, or Permian-Triassic mass extinction, around 252 million years ago. This cataclysmic event, which remains the largest extinction in Earth's history, led to the disappearance of almost 90% of marine species and 70% of terrestrial species. This radical change in climatic and environmental conditions rendered the planet almost uninhabitable for the majority of life forms, transforming Pangea into an arid desert world. However, despite this generally warm climate, there were regional differences, particularly in the distribution of precipitation. Climatic variations were largely influenced by Milankovitch cycles, periodic oscillations linked to the Earth. These cycles include the precession of the Earth's axis and the eccentricity of its orbit, modifying the amount of sunlight received by different regions of the globe. During the late Triassic, regions close to the equator received more sunlight, increasing the energy available to generate more frequent precipitation. Conversely, higher latitudes with less sunlight experienced less precipitation. Pangea's ecosystems were characterized by unique geological and climatic conditions, profoundly influencing biodiversity and species interactions. The supercontinent Pangea, which encompassed all land masses, extended mainly around the equator. Pangea's climate was marked by a wide variety of extreme conditions. Indeed, the assembly of Pangea led to increasingly arid climates, especially inland, where rainfall was less frequent due to the great distance from the oceans. The assembly of Pangea had profound repercussions on the evolution of life at that time, modifying both terrestrial and marine environments. When the continents united to form this immense single landmass, the extent of seacoasts diminished considerably. The reduction in coastal zones, usually rich in biodiversity thanks to the transition between marine and terrestrial environments, impoverished coastal marine ecosystems. It has also led to a redistribution of marine life towards new ecological niches. As a result, Pangea was home to rich, diverse ecosystems along its coasts. Seasonal variations were pronounced, resulting in particularly hot summers and harsh winters, a direct consequence of Pangea's immense size. However, the coastal margins, especially near the Tethys Ocean, enjoyed a more temperate and humid climate. These regions were more suitable for vegetation, with forests and fertile land. Pangea didn't just shape the continents as we know them today. It was also the cradle of a major biological transformation, enabling new forms of life to flourish in an ever-changing world. The center of the supercontinent, far from the oceans, was subject to intense aridity, characterized by a desert climate. Indeed, the enormous distance separating these regions from sources of moisture created vast desert zones. These dry conditions favored the evolution of amniotes, a group of animals that included the ancestors of reptiles, birds, and mammals. Amniotes were distinguished by the ability of their eggs to be laid on land, far from aquatic environments, thanks to the presence of an amniotic membrane protecting the embryo from dehydration. This reproductive advantage enabled them to expand into more arid areas where amphibians, which depended on water for reproduction, could not survive. Increasing aridity was particularly marked in western Pangea, which became a major focus of amniote evolution and diversification. These animals adapted to a multitude of dry habitats, evolving to better survive in harsh climatic conditions. Western Pangea also played an interesting role in the geographic spread of amniotes, which expanded their territory as environmental conditions favored their development. By contrast, the interior of Pangea was marked by climatic extremes. These conditions were reflected in the evolution of living organisms such as Prehistories, hardy herbivorous reptiles whose bones show irregular growth patterns. These patterns indicate that Prehistories had to cope with periods of intense environmental stress, probably linked to climatic fluctuations, such as prolonged droughts or periods of high heat. Furthermore, the excessive heat of this area was essential for the dinosaurs, as these cold-blooded giants depended on ambient heat to regulate their body temperature. During the late Triassic, the distribution of precipitation played a crucial role in the differentiation of habitats between mammals and reptiles on the supercontinent Pangea. Transversidont cynodonts, the ancestors of mammals, populated tropical regions characterized by a monsoon climate with biannual rainfall, which favored their development. In contrast, further north in temperate zones, lived the procolophonids, a group of reptiles better adapted to conditions where heavy rains occurred only once a year. This difference in rainfall patterns was a determining factor in the geographical distribution of the two groups. Mammals, requiring an abundance of water for their survival, were naturally restricted to areas rich in precipitation. This is due in part to the way their bodies process waste, which makes them more dependent on water, unlike reptiles, which were better able to adapt to more arid environments. This physiological difference gave reptiles a competitive advantage in regions where water was scarcer, notably in temperate zones further north of Pangea. Consequently, reptiles did not migrate to equatorial regions, having already found their niche in environments where climatic conditions were more favorable. Moreover, the absence of ocean barriers on Pangea created a unique environment where species could theoretically disperse freely across this immense unified landmass. This phenomenon favored Cosmopolitanism, a mode of geographic distribution in which certain successful species achieve a wide distribution and end up occupying various ecological niches across Pangea. Cosmopolitanism enabled certain species to expand their range opportunistically, adapting their survival to the varied environmental conditions of the supercontinent. Similar plants and animals were found in territories now separated by oceans. In addition, the terrestrial fauna, unified by this continuity, showed marked similarities. Amphibians, reptiles, and the first dinosaurs migrated freely across the continent, forming a relatively homogeneous ecosystem. At the same time, plant diversity, influenced by climate, showed contrasts. While conifers, giant ferns, and other drought-resistant plants dominated arid zones, wetter regions were home to thriving dense forests. Mass extinctions, particularly those of the Permian-Triassic and Triassic-Jurassic periods, also played a major role in the rise of cosmopolitanism. The Permian-Triassic extinction left a vast ecological vacuum, allowing some hardy species to spread rapidly across Pangea. Among these species, Lystrosaurus, a herbivorous reptile belonging to the Therapsid group, took advantage of this critical event and spread to almost all regions of Pangea. This phenomenon, known as catastrophe fauna, refers to a community of species with low diversity, but capable of spreading massively in the available habitats after a biological crisis. Lystrosaurus is an emblematic example, becoming one of the few species to thrive in a world almost devoid of life. Despite this favorable cosmopolitan background, archaeological and paleontological evidence reveals that many Pangean species had a limited geographic distribution. This phenomenon is known as provincialism. Although physical barriers such as oceans and mountain ranges were largely absent, other factors limited species dispersal. One of the main reasons for this was the extreme climatic variations that characterized Pangea. The climate was strongly influenced by the monsoon, a seasonal phenomenon characterized by persistent winds, generally linked to wind inversions between oceanic and continental zones. This phenomenon created vast differences between regions near the equator and those closer to the poles. These climatic variations were accentuated by very marked seasons and differences in latitude, making certain regions inhospitable to species adapted to other environmental conditions. For example, pteridosperms, primitive seed plants, are a good illustration of this trend. These plants had developed specific adaptations to cold environments, particularly in the regions of Gondwana, the southern part of Pangea. Even without physical barriers, cold-adapted pteridosperms were unable to spread beyond southern regions. This was due to the hot, humid climates that prevailed in the equatorial zones. This climatic difference prevented northward dispersal and contributed to maintaining a certain ecological isolation between Gondwanan species and those of more northerly regions. Similarly, during the Triassic period, pteridosperms from northern regions came to dominate Gondwanan ecosystems, probably taking advantage of climate change or local extinctions to establish themselves. One of the major consequences of the formation of Pangea is its potential impact on mass extinctions, particularly in the Permian-Triassic period. One of the hypotheses put forward is that the tectonics and geography of Pangea contributed to aggravating this mass extinction by modifying coastal and marine environments. The merging of the continents considerably reduced the surface area of the continental shelves, the shallow areas at the boundary between land and ocean. These shelves were home to marine ecosystems with a particularly remarkable wealth of biodiversity. Reducing the habitats of these shelves could have made marine species more vulnerable to extinction by limiting their ranges and concentrating them in smaller areas. This would have increased their exposure to environmental disturbances, such as temperature variations, changes in oxygen levels, or modifications to ocean chemistry. However, while this theory is attractive, the evidence for a species area effect, which suggests that a reduction in habitat size leads to a proportional decrease in species diversity, is not clearly established in the more recent and better documented parts of the geological record. Uncertainties therefore remain as to this relationship. It is therefore difficult to assert that the reduction in the surface area of continental shelves played a direct and decisive role in the mass extinctions. Nevertheless, it is likely to have weakened marine ecosystems prior to the Permian-Triassic crisis. Another interesting hypothesis concerns the link between the reduction in seafloor spreading and the Permian-Triassic extinction. The formation of Pangea slowed the expansion of mid-ocean ridges, areas where the ocean floor is formed by volcanic activity. As a result, the oceanic crust cooled and subsided, causing sea levels to fall. This process may have reduced the number of islands and isolated marine habitats that could have served as refuges for marine species in the face of environmental disturbance. Marine species, already facing difficult living conditions due to the reduction in coastal habitats, would therefore have seen their refuges disappear, increasing their vulnerability to extinction. In addition, The formation of Pangea led to a mixing of species from different continents that had previously been separated. This phenomenon, while it may have created new ecological interactions, could also have reduced biological diversity by eliminating endemic species that were adapted to specific ecological niches. This could have contributed to a gradual decline in species diversity long before the mass extinctions, weakening ecosystems and making them more susceptible to collapse during environmental crises. Despite this trend towards species cosmopolitanism on Pangea, climatic barriers continue to separate different ecological communities. Although geographically unified, Pangea was subject to strong climatic variations depending on latitude and season. These variations prevented certain species from spreading throughout the supercontinent. Extreme climatic conditions, such as intense monsoons and temperature variations between equatorial and polar regions, helped maintain a certain provincialization of species. This meant that certain ecological communities remained localized in specific areas, limiting the overall mixing of species across Pangea. Some continental refugia may have disappeared during major volcanic episodes, such as the eruptions of the Amishan Traps, a vast complex of lava flows in southern China. This region, one of the few not to have merged with Pangea, could have served as a refuge for certain marine and terrestrial species. However, the eruptions of the Amishan Traps, which occurred before the Permian-Triassic extinction event, probably destroyed this refuge zone. This exacerbated the global ecological crisis by depriving species of a final sanctuary. At the end of the Mesozoic, Pangea began to fragment, causing the land masses that form today's continents to separate. This division profoundly transformed the evolution of ecosystems as species, now isolated from each other, began to evolve separately on each continent. This fragmentation led to increased diversification of terrestrial life, with each region developing unique characteristics in response to its new environment. During the time of Pangea, particularly in the Carboniferous period, lush, dense vegetation dominated the landscape, providing a rich habitat for a diverse fauna. This vast territory, which extended over a large part of the globe, featured considerable climatic variations from one region to another, ranging from humid tropical zones to arid deserts. These contrasts gave rise to a wide variety of ecosystems, each hosting plant species adapted to local conditions. Carboniferous forests were mainly composed of giant lycophytes, some of the earliest vascular plants, which initially dominated the Pangean landscape. They formed vast forests across the supercontinent, with much larger species than today. The genus Lepidodendron, often called the scale tree because of its scale-covered stems, could reach impressive heights, sometimes up to 40 meters or 130 feet. They thrived in swamp forests in the Paleozoic, but gradually disappeared towards the end of the Permian due to climatic and geological changes. It's worth noting that trees of the Lepidodendron genus were involved in the formation of coal deposits in this period. In addition, there were sphenophytes such as calamites, fossil plants close to horsetails, which formed trees 5 to 10 meters or between 15 and 30 feet tall, with ringed segmented stems. These plants thrived in marshy areas, ideal for fossilization. Meanwhile, ferns were another major group in the flora of Pangea, with a wide variety of types, including tree ferns like Soronius, which reached heights of up to 10 meters or 30 feet. On the other hand, species such as tree ferns of the Dicksonia genus reach several meters in height and form dense forests, particularly in humid regions of the supercontinent. This group of plants, still present today, played a key role in structuring the ecosystems of the time. Towards the end of the Carboniferous, a major evolution occurred with the appearance of seed ferns, or teratospermophytes, which marked a transition from spores to seeds, enabling plants to move away from humid environments. In fact, seed plants took advantage of the arid conditions that prevailed on Pangea. Seeds, which contain a reserve of nutrients and are protected by a tough envelope, enabled plants to reproduce in dry environments, where spore-bearing plants such as ferns were at a disadvantage. The Glossopteris genus, for example, was widespread in the southern regions of Pangea, particularly on the supercontinent Gondwana, where it formed immense forests. This genus is best known for its tongue-shaped leaves, which can measure from 2 to 30 centimeters, or 0.8 to 12 inches in length. These plants contributed to the evolution of terrestrial ecosystems before disappearing during the Great Extinctions. Glossopteris fossils also play an essential role in our understanding of ancient flora and plate tectonics, since they testify to a formerly warmer climate and a distribution linked to the supercontinent Gondwana. As the climate changed at the end of the Carboniferous and into the Permian, with periods of glaciation and warming, new species appeared. These included the cycads and chordates, which formed large forests. These palm-like gymnosperm plants thrived in tropical and subtropical climates. The genus Cycas, which still exists today, is one of the living witnesses to this flourishing period. The Permian also saw the birth of the ginkgos, represented by species such as ginkgo biloba, which were also present on the supercontinent. These trees, resistant to changing climatic conditions, survived several mass extinctions, demonstrating their remarkable capacity for adaptation. Gymnosperm forests, which were dominant at the time, are also showing signs of adaptation to extreme conditions. Gymnosperms are seed plants that thrive in relatively dry environments, and their growth reflects the arid conditions that prevailed in the interior of Pangea. Towards the end of the Pangean era, conifers began to emerge and diversify the landscape. These plants, with their cones and needles, marked a significant evolutionary advance and were particularly well adapted to drier climates. These forests were often subject to periods of rapid growth followed by periods of stagnation due to seasonal climatic fluctuations or unpredictable weather conditions. The evolution of gymnosperms in such an environment enabled their survival and diversification despite the unfavorable conditions within Pangea. These species would endure, diversify throughout the Mesozoic, and invade the planet. Humid equatorial regions favored the growth of lush forests. Genera such as Araucaria and Podocarpus appeared in temperate and subtropical climates. Coal marshes, also known as peat swamps, form mainly in regions of constant high humidity, generally located near the equator. These environments, rich in vegetation and decomposing organic matter, are ideal sites for the formation of coal, a process that can last millions of years. However, the assembly of Pangea profoundly disrupted the climatic and environmental conditions that favored the formation of these marshes, leading to a drastic drop in coal deposition. One of the main reasons for this decline is the disruption of the Intertropical Convergence Zone, a region of low pressure near the equator where trade winds meet, resulting in regular rainfall. Due to the vast extent of Pangea, this zone has been greatly modified, affecting the distribution of precipitation across the supercontinent. The climate became drier inland, and even regions close to the equator, once ideal for coal swamp, saw their humidity diminish. The assembly of Pangea created extreme monsoonal climates, where dry and wet seasons were intensified, making conditions unfavorable for the continued formation of swamps rich in organic matter. These drastic climatic changes led to a reduction in coal deposition to historically low levels over the last 300 million years. During the Permian, a geological period that stretches from around 298 to 251 million years ago, coal swamps were almost absent on Pangea itself. Coal deposition, once widespread, was largely confined to the microcontinents of North and South China. These regions were not yet fully integrated into Pangea, which enabled them to retain more stable and humid environmental conditions, favorable to coal formation. During the Pangean period, terrestrial and marine fauna underwent marked diversification, a direct consequence of the supercontinent's formation at the end of the Paleozoic and its existence at the beginning of the Mesozoic. This geographic configuration has shaped habitats, fostering the emergence and adaptation of numerous species. The tropical oceans of Pangea teemed with life, from primitive fish to large marine reptiles. The Tethys Ocean, to the east of Pangea, was home to exceptional marine biodiversity. Coral reefs thrived there, as did large marine predators such as ichthyosaurs and plesiosaurs, forming a rich and dynamic ecosystem. At the same time, the marine fauna of this period had to constantly adapt to the significant variations in sea level caused by climatic fluctuations. Ammonites, marine mollusks with spiral shells, populated these waters in abundance, while brachiopods, filtering water to feed, were attached to underwater rocks. Ichthyosaurs, dolphin-like marine reptiles, hunted in the supercontinent's tropical seas. They were the first pelagic reptiles, fully adapted to life, not only in coastal waters, but also off the coast of Pangea. Ichthyosaur fossils have even been found at high altitudes, indicating that their marine habitat was once very different. In these aquatic environments, various fish species were widespread, testifying to the incredible adaptability of marine organisms in these changing ecosystems. The actinopterygians, ray-finned fish, dominated the seas and lakes, while the sarcopterygians, flesh-finned fish, foreshadowed the tetrapods. Their more adaptive forms enabled them to evolve in the rivers and lakes of the supercontinent. These marine creatures thrived in the shallow seas surrounding Pangea and played a central role in the ecosystems of the time. Towards the end of the Triassic period, reptiles, initially small in size, gradually evolved, giving rise to the large dinosaurs emblematic of the Mesozoic. This evolution testifies to the diversity and adaptability of the species that populated Pangea. Among them, the therapsids, ancestors of the mammals, stood out. They included predators, such as gorgonopsians, and herbivores, such as diconodonts, which thrive thanks to their adaptation to the arid environments of Pangea. Archosaurs appeared at the end of the Permian, giving rise to lineages that would lead to dinosaurs, pterosaurs, and crocodilians. Among them, species such as Herrerasaurus and Euraptor, small bipeds, represented the first dinosaurs. At the same time, heavier, herbivorous reptiles such as periosaurs played an essential ecological role. This diversification of reptiles was accompanied by a notable presence of amphibians, notably temnospondyls, large aquatic carnivores like eriops that dominated swamps. At the same time, the smaller lepospondyls populated the freshwaters of Pangea, playing an ecological role similar to that of modern salamanders. While reptiles and amphibians dominated dry land and aquatic environments, mammal ancestors such as cynodonts began their evolution at the end of the Permian. These small omnivores or insectivores gradually adapted to the changing conditions of the supercontinent. These small animals would gradually evolve to give rise to the first true mammals, such as Morganocaudontidae, towards the end of the Triassic. But that's not all. Pangea was also home to a fascinating air life. At the same time, insects proliferated in this diverse environment. Creatures such as Meganeura, a giant dragonfly, hunted in swamps, while beetles and orthopterans like locusts adapted their diets to Pangea's vegetation. Although birds didn't emerge until the Upper Jurassic, some flying reptiles such as pterosaurs were already appearing during the Pangean era, anticipating the evolution of creatures capable of flight. The first dinosaur ancestors, like Colophysis, inhabited the vast desert and semi-arid plains of Pangea. They thus paved the way for the future reign of the dinosaurs, which would only fully assert itself after the fragmentation of the supercontinent. Forests of cycads and conifers provided the ideal backdrop for the dinosaurs that ruled the Earth at the time. Among them were iconic species that dominated terrestrial ecosystems for millions of years. It was also during this period that the first true mammals appeared, albeit small and modest compared to the mighty dinosaurs. Nevertheless, these mammals foreshadowed the advent of more evolved groups that would diversify after the disappearance of the dinosaurs. The fauna of Pangea illustrates a period of exceptional richness, marked by constant diversification in response to environmental change. It should be noted that Pangea was the scene of the greatest mass extinction in Earth's history, which occurred at the end of the Permian, triggering a radical transformation of Pangean ecosystems. Subsequently, the recovery of ecosystems was extremely slow, spanning several million years. However, this period of recovery also marked the emergence of the first dinosaurs and primitive mammals, initiating a new phase in the evolution of life on Earth. The breakup of Pangea took place in three major phases, each contributing to the formation of the oceans and the gradual separation of the continents. The first phase, beginning in the Middle Lower Jurassic, marks the start of the breakup, with the creation of a major fault between the Tethys Ocean to the east and the Pacific Ocean to the west. This geological fracture occurred mainly between the tectonic plates of North America and Africa, triggering the appearance of several secondary faults, the most important of which is the Mississippi River Fault. This process eventually led to the birth of a new ocean, the Atlantic. However, the opening of the Atlantic Ocean was not uniform. It began in the north-central Atlantic region, while the South Atlantic remained closed until the Cretaceous. During this period, Laurasia, the supercontinent uniting North America and Eurasia, began a clockwise rotation. This movement caused North America to move northwards and Eurasia to move southwards. This rotational movement also initiated the gradual closure of the Tethys Ocean, a key event that profoundly influenced the future geography of the Mediterranean region in the Middle East. Meanwhile, other tectonic changes were taking place on the opposite side of the African continent. Along the adjacent margins of East Africa, Antarctica, and Madagascar, new tectonic faults were forming, heralding the future opening of the Southwest Indian Ocean. These fractures gradually separated Africa from Antarctica and Madagascar, giving rise to this ocean during the Cretaceous period. The second major phase in the fragmentation of Pangea began in the early Cretaceous, around 150 to 140 million years ago, marking a key stage in the Earth's geological evolution. During this period, the supercontinent Gondwana, which included Africa, South America, India, Antarctica, and Australia, began to split into several blocks. This separation was decisive in the formation of the continents we know today. This process began with the collision of the minor continent of Cimmeria with Eurasia around 200 million years ago. This collision gave rise to a subduction zone called the Tethyan Trough, which probably played a key role in the reduction of the Tethys Ocean, a vast inland ocean at the time. This subduction may also have led to the northward displacement of continental masses such as Africa, India, and Australia. These tectonic movements accentuated the separation between Western Gondwana, comprising Africa and South America, and Eastern Gondwana, including Antarctica, India, and Australia. This division led to the formation of a new ocean, known as the South Indian Ocean. As this split progressed, the South Atlantic Ocean began to form. This process did not proceed uniformly. The opening of the South Atlantic followed a particular dynamic, evolving from south to north like a geological zipper. South America began to move away from Africa, gradually opening up this ocean, which became a major corridor for oceanic communication between the southern and northern hemispheres. At the same time, Madagascar and India began their own separation from Antarctica, opening up the Indian Ocean. While Madagascar finally came to a standstill after joining the African plate, India continued its rapid northward migration at an exceptional rate of 15 centimeters per year, or 6 inches a year, gradually closing the Tethys Ocean. This rapid advance of India towards Eurasia would lead millions of years later to the formation of the Himalayas, the result of the collision of these two tectonic plates. In the late Cretaceous, some 100 to 90 million years ago, India and Madagascar finally separated from each other. While India continued its northward course, Madagascar locked onto the African plate, stabilizing itself on the east coast of the African continent. During this period, Australia also began to separate from Antarctica and migrate northeastwards. This tectonic shift led to the formation of the Coral Sea and the Tasman Sea. It also led to the separation of New Zealand and New Caledonia, which then moved eastwards to become independent islands in the Pacific Ocean. The third and final major phase in the breakup of Pangea took place at the beginning of the Cenozoic, a period stretching from the Paleocene to the Oligocene, marking a significant transformation in the Earth's geological configuration. During this period, North America and Greenland began to break free from Eurasia, leading to the opening of the Norwegian Sea some 60 to 55 million years ago. This separation was accompanied by the continued expansion of the Atlantic and Indian Oceans, contributing to the closure of the Tethys Ocean. Simultaneously, Australia also experienced a separation from Antarctica, moving rapidly northwards, just as India had done over 40 million years earlier. Today, Australia and India are moving northeastwards at an impressive rate of 6 centimeters per year, or 3 inches per year. Antarctica, meanwhile, has been located near or at the South Pole since the formation of Pangea some 280 million years ago. This geographical position has had major consequences for the region's climate and glaciation. The collision between India and Asia began around 60 million years ago, leading to the formation of the Himalayan mountains. This major geological event not only sculpted the landscape, but also led to the definitive closure of the Tethys Sea. This collision continues today, with India continuing to move northwards, reinforcing the region's tectonic plate dynamics. At the same time, the African plate has begun to change direction, shifting from a westerly to a northwesterly movement towards Europe. Meanwhile, South America also began to move northwards, separating from Antarctica. This movement enabled full ocean circulation around Antarctica for the first time. This led to rapid cooling of the region and the formation of glaciers, marking a turning point in the Earth's global climate. During this period, several other notable geological events took place, such as the opening of the Gulf of California, the uplift of the Alps, and the formation of the Sea of Japan. These changes not only altered the planet's topography, but also had significant impacts on biodiversity and marine and terrestrial ecosystems. Currently, the breakup of Pangea continues in the East African Rift, an area where tectonic plates continue to separate, suggesting that ongoing collisions could indicate the formation of a new supercontinent in several 100 million years' time. The breakup of Pangea, which began in the mid-Jurassic, marked another major transformation for life on Earth. This process fragmented the supercontinent into smaller blocks, which would later become the continents we know today. At this time, the oceans were dominated by mollusks, notably ammonites, as well as impressive marine creatures such as ichthyosaurs, fish-like marine reptiles, sharks, rays, and the first ray-finned fish, ancestors of modern fish. Geologists argue that the formation of Pangea played a significant role in the mass extinction that occurred at the end of the Permian, a particularly devastating event for marine life. As Pangea formed, the extension of shallow water habitats diminished considerably, with dramatic consequences for marine ecosystems. The creation of vast land barriers prevented the circulation of cold polar waters towards tropical zones. This has led to a reduction in dissolved oxygen levels in the remaining warm water habitats, exacerbating the ecological crisis and contributing to the loss of around 95% of marine species diversity. In contrast, the breakup of Pangea led to environmental transformations that favored the emergence of new shallow water habitats. As the total length of coastline increased, numerous new marine environments were formed, offering opportunities for marine life to thrive once again. The opening of channels between small land masses also allowed warm and cold ocean waters to mix, promoting marine diversity and the emergence of new species. On land, the fragmentation of Pangea had a major impact on plant and animal populations. By separating these groups into newly isolated continents, the breakup encouraged the development of unique adaptations to their new environments. These adaptations, resulting from selection pressure in distinct habitats, contributed to an increase in biodiversity. The species that survived this period evolved in response to varied ecological conditions, giving rise to unprecedented biological richness in many ecosystems. The breakup of Pangea had profound consequences for terrestrial and marine biodiversity. Firstly, the fragmentation of the continents led to the geographical isolation of many species. As the continental masses separated, they created new physical barriers, such as oceans, mountains, and deserts, which led to the appearance of new species through a process known as speciation. Animal and plant populations, isolated in their respective environments, evolved differently, promoting biological diversification. For example, Australian mammals such as marsupials developed independently of those on other continents. At the same time, changing climates and habitats became an inevitable consequence of dislocation. Pangea, previously dominated by vast deserts, saw the emergence of a greater variety of regional climates due to the fragmentation of the continents. This allowed the development of different ecosystems, such as tropical forests, grasslands, and temperate zones. The creation of new coastlines has multiplied marine habitats, contributing to the growth of coral reefs, mangroves, and other coastal ecosystems, thus increasing marine species diversity. However, not all species have benefited from this dynamic. While some succeeded in colonizing new territories, others faced extinction due to their inability to adapt to these new environmental conditions. The newly formed continents also brought species from different horizons into competition, as happened when North and South America were linked by the Isthmus of Panama. The breakup of Pangea also altered oceans and ocean currents, creating new marine ecosystems and disrupting existing biological interactions. New ocean currents redistributed nutrients and influenced water temperatures, prompting the emergence of new marine species adapted to these changing environments. The separation of continents has influenced food chains as organisms have had to adapt to new food resources and different environments. Vegetation diversity and geographic fragmentation led herbivores and their predators to evolve together in specific ecological niches, shaping distinct ecosystems. These transformations have had a long-term impact on today's flora and fauna. Modern biogeographical regions such as the Neotropics, Ethiopia, and Australasia are the result of this geological reorganization. The breakup also contributed to the appearance of endemic species, such as Madagascar's lemurs and Australia's kangaroos, which developed in isolated environments. The breakup of Pangea had a profound impact on the evolution of global biodiversity, promoting speciation, modifying habitats and climates, and reshaping food chains. The impact of this major geological event is still visible in the current distribution of species across the planet. Although Pangea disappeared millions of years ago, its legacy remains deeply rooted in the landscape, species, and even climates of today's Earth. Its history reminds us just how much our planet is in perpetual transformation, a never-ending journey through time. If the Triassic and Jurassic eras saw a great deal of upheaval and just as much radiation, the Cretaceous is no exception. It too is characterized by a large number of major biological evolutions and milestones in both the plant and animal worlds. While the flora and fauna of the Cretaceous are eager to tell us their story, let's take a look at the Cretaceous from a geological perspective. The Cretaceous is a long period, the longest of the entire Mesozoic, in fact, spanning some 185 million years, with the Cretaceous alone already representing 80 million years. The Cretaceous is the last system of the Mesozoic and extends from around 145.5 million years ago to 65.5 million years ago. It is subdivided into two subsystems. In geology, we speak of the Lower Cretaceous, which includes the Berriasian, Valanginian, Hauterivian, Birimian, Aptian, and Albian stages. Next comes the Upper Cretaceous, which includes the Cenomanian, Turonian, Coniacian, Santonian, Campanian, and Maastrichtian stages. For the record, the characteristic rock of the Cretaceous period in northern Europe, chalk, is called Creta in Latin. It was from this Latin origin that the period took its name. As you can see, this period is long and divided into numerous subsystems, 12 in all. Each has its own particularities. Over millions of years, the face of the Earth changes in step with its geological activities. Let's take a closer look together. We left behind a rather warm and humid environment in the previous period, the Jurassic. For the moment, the changes are still quite minimal and difficult to perceive. After a cooling period in the early Cretaceous, the climate becomes warm and humid again. At the end of the Cretaceous, temperatures average 20 degrees Celsius or 68 degrees Fahrenheit. By way of comparison, in 2024, we recorded an average temperature of around 15 degrees Celsius or 59 degrees Fahrenheit on Earth. But that's not all. As you can see from this representation, there are still no ice caps. This means that the climate is still relatively warm, as it was for much of the Jurassic period. Remember, not so long ago, there was a single continent on Earth called Pangea, but in the course of previous eras and climatic and geological upheavals, this continent broke up. The emerged lands, heckled by the Earth's internal activities, gradually fractured. Two continents emerged, Laurasia to the north and Gondwana to the south. But as you can imagine, towards the end of the Jurassic and the beginning of the Cretaceous, the continental waltz was far from over. In fact, it's still going on today. While the northern part of the planet has already continued its slow dislocation in the Cretaceous, new continents are also appearing in the south. If you take a close look at our planet at that time, you'll probably notice a few similarities with our current geographical situation. For the first time in Earth's history, the face of our beautiful blue planet looks a little more familiar. Speaking of the blue planet, as you know, most of our planet is covered by water. Look at that vast ocean we're flying over. It's impossible to see this detail with the naked eye, but it's very important. In the upper Cretaceous, sea level was much higher than it is today. To be precise, it was 300 meters, or 1,000 feet, above today's level. This changes many things. Some of today's land masses were drowned under the waves at that time. This is true of a large part of Europe, which unlike today formed a kind of archipelago. This high sea level also had an impact on the climate. So far, we've seen that vegetation in the Triassic and Jurassic periods in particular was flourishing and luxuriant. In fact, this is what enabled multiple species to grow, evolve, and develop. Up to now, the plants we've come across in earlier periods have mainly been conifers, which are also very varied, and ferns, which are just as diverse. But during the Cretaceous period, thanks to a climate that favored their evolution, plants underwent an evolutionary radiation that would forever mark the history of plants. Angiosperms made their grand entrance onto the plant scene. What does angiosperm mean? This term defines flowering plants. Now imagine how spectacular and extraordinary this change was for flora and fauna. Until now, plants were made up entirely of leafy species, some of which use cones, hence the name conifers, to reproduce. With the arrival of angiosperm plants, vegetation took an unprecedented turn, opening up new prospects for evolution. Flowers were added to the existing plant cover, and with new plant species come new ecological niches. Some insects will take advantage of this opportunity to diversify and take advantage of these famous angiosperm plants. By the end of the Cretaceous, these plants had become the dominant plant group. One of the oldest is Archifructus, an aquatic plant. It is found in lakes and ponds. There are 3 known genera of Archifructus: Archifructus eoflora, Archifructus lianengensis, and Archifructus sinensis. They all have roots, lacy leaves characteristic of aquatic plants, flowers, and seeds. These plants generally measure less than 50 centimeters or 20 inches in height. As far as reproduction is concerned, these flowers fall into 2 categories. The first, counting Archifructus, lianengensis, and sinensis, has a male pollen-bearing plant and a female ovule-bearing plant. For eoflora, it's a little different. It includes both sexes. It is said to be bisexual. Montesecchia vidali is another aquatic plant. It was discovered in the Spanish Pyrenees, but was generally widespread in the Iberian chain throughout the Cretaceous period. Fossil specimens can be found in the province of Cuenca at the Las Hoyas site, for example. For the record, the latter has given paleobiologists and scientists a bit of a headache when it comes to classifying it. Fern, moss? In the end, none of the above. After several decades of putting the pieces together, it turns out to be an aquatic plant, and if the latest hypotheses are to be believed, probably one of the very first flowering plants on our planet. We owe this revelation to 2 great European scientists, Bernard Gomez and Veronique de Viero. Thanks to advances in analytical procedures and techniques, scientists can now put forward new hypotheses and study fossils in a whole new light. For this plant, for example, Bernard Gomez uses hydrochloric acid in very small quantities. Dosed meticulously, drop by drop, it brings to light a few millimeters of plant. It's as if a mummy of Montesecchia appeared after the scientists' work. From then on, new elements become perceptible, notably the plant's stomatal apparatus, which was previously undetectable. Why focus on this anatomical part in particular? Because it reveals the holes through which plants have collected the carbon dioxide around them. As with animals, these holes and the way they function will be very different in terrestrial and aquatic species. In the case of Montesecchia, the stomatal apparatus is perfectly compatible with an aquatic lifestyle. We can also see that this is an angiosperm plant, since the process also reveals fruits with a protective envelope called a carpel, which protects a single seed. These plants also benefit from smaller leaves, a much greater number of stomata and veins, and more efficient transpiration and photosynthesis rates. This type of plant has developed these capabilities, notably the fruit and the protective envelope for the seed and pollen, because the aquatic environment is hostile to these seeds. Thanks to the carpels, the seed is protected. During the Middle Cretaceous, as the climate warmed and sea levels rose, angiosperms occupied lowland undergrowth for the first time, in competition with ferns and conifers. Perhaps this is why plants evolved. Ongoing research will no doubt tell us more about this in a few years' time. However, if there's one thing that's certain, it's their usefulness in the ecosystem. The first to benefit from this new ecological niche are pollinating insects. In biology, we speak of coevolution. In other words, two species influence each other. There's competitive coevolution, in the case of the binomial prey-predator or host-parasite, and there's cooperative coevolution in the case of mutualist species, which is our case here. In this environment, already rich in flora and fauna, the pressure to make a place for oneself in the cycle of life is very strong. However, plants and insects form a strong team and will conquer almost all environments. Flowering plants need insects to thrive, so they need to attract them. To do this, and to be sure of attracting them, they will learn to show off. They'll sport pretty, colorful petals, shapes a little more extravagant than usual, exhale sweet perfumes, and even produce a sweet nectar that insects can't resist. Butterflies, wasps, and other insects already present are thus enriched with new traits adapted to their new environment. For example, nectar-sucking tubes gradually replace the mandibles of some butterflies. Angiosperms can also contain poisons, more often than gymnosperms, the plants with ovules. For them, it's a form of protection. But insects that manage to digest them benefit from new resources without competition. The bee, or at least its closest ancestor, also appeared during this period. The bee in question is Meletosfex burmensis. This insect is tiny, barely 3 millimeters. On more than one occasion, we've been surprised by the exceptionally large size of certain insects at one time. But in the case of our Meletosfex, it's quite the opposite. Its small size compared with our current specimens is quite astonishing. It belongs to the superfamily Apoideae, whose ancestors date back to the Jurassic period. In terms of physical characteristics, it's somewhere between a wasp and a bee. For example, its silhouette and anatomy are very similar to those of a wasp. But it also has branched hairs, which this time are more comparable to those of the bee. This Meletosfex found itself trapped in the resin of this plant. Unfortunately for him, he's living out his final hours. But we'll find him in amber, the fossilized resin in present-day Burma, in the Hukong Valley. He will become a privileged witness to the Cretaceous. He won't be alone, as other insects have suffered the same fate here. The ones you can see agglomerated with this amber are two species of ant. The first is called Hydomyrmecini. They're also known as hell ants. The second is the unicorn ant. Both will be found millions of years from now by researchers. Observing them on the same fossil site is a reminder of their kinship. The Apoidean family's closest relatives just happen to be ants. But back to our potential bee ancestors, Meletosfex, and pollinating insects. Initially, these insects were carnivorous and probably quite solitary. Then they specialized by type of flower. But of necessity, in order to adapt and survive, it's well known that there's strength in numbers. Eusociality thus became their best asset. Depending on their caste, insects specialize not by type of flower, but rather by usefulness to the colony. Some take care of the larvae, others build the nest, others defend it or go off in search of food. It wasn't until a few million years ago, in the mid-Cretaceous to be precise, that specimens capable of this kind of social prowess appeared. They belong to the corbiculate tribe. This tribe included no fewer than 1,000 different species. While eusociality is a major development in some insects' ability to survive and adapt to their ecosystems, others have found quite different ways. Dragonflies and stick insects, such as Cretophasmomina, melanogramma, prefer mimicry. They try to blend into the background to escape the sight of predators. This is also very effective. Some are such kings of camouflage that they are almost imperceptible to the untrained eye. Another way out is to live at night. At least that's what some specimens thought. No doubt they thought they could avoid predators, which are normally less active at this time of day. Once the ball of flying reptiles was over, and the tree-dwelling animals asleep, these insects were free to roam as they pleased. Once the heavy march of the giant dinosaurs was over, it was soothing to return to the calm of the night, don't you think? Between those big predators, the pterosaurs that crisscross the sky, the tree-dwelling animals, veritable forest flyers with insatiable appetites, danger seems to lurk everywhere. Now that the moon has taken over from the sun, there's only silence surrounding us and the stars gazing down on us. All seems calm. Herbivores, carnivores, and insectivores are plunged into a deep, restorative sleep. All of them? Not quite. Look closely at the ground. Can't you detect the slight rustling and subtle movements in the undergrowth? It's a small mammal living in this vegetation cover, and it's probably just beginning to appear. It's rather stealthy, so you'll have to be quick and very observant to be lucky enough to catch a brief glimpse. It only dares to venture out of its nest at nightfall. He's sure to enjoy a hearty meal of insects of all kinds. It's easy to forget, when we think of the Mesozoic era still associated with dinosaurs reigning supreme over the land, that dinosaurs were far from the only inhabitants of our planet. While it's true that the dominant species during the Cretaceous remains the dinosaur, mammals still manage to make their mark on our world. Their way of life and physical capacities, at first sight rather weak compared to the dinosaurs, will ultimately be their greatest asset in resisting the mass crisis that will be raging in a few million years' time. But more on that later. For now, let's get back to our insects and our new plants. Insects are taking full advantage of the arrival of angiosperm plants, but they are far from being the only Cretaceous novelties. During this period, lianas, new types of shrubs and herbaceous plants, can be seen at the heart of this impressive forest. Time and again during our travels, we have seen that the use of the term herbivore was a mistake. Minimal perhaps, but a mistake nonetheless. Let's just say it was an abuse of language. To be perfectly accurate, the animals that preceded the Cretaceous period were vegetarians, not herbivores. Indeed, grass had not yet appeared on Earth. In the Cretaceous, however, things are a little different. Yes, herbaceous plants also made their grand entrance into the already rich realm of terrestrial vegetation, and the least we can say is that they too will manage to carve out a place for themselves within the plant kingdom, offering new opportunities for the animal world. Although they don't benefit solely from these plants, many snake species find camouflage and small prey in these herbaceous plants. These animals tend to be found in the humid forests of Laurasia. Before they took on the shape we know today, the first snake-like animals had legs at the back of their bodies. They were not very well developed, but were sufficiently articulated to move along the herbaceous carpet. They have an ankle and even a few toes. This is the case of Najash rheanagrina, a species of snake that still has its famous hind legs. It prefers to hunt at night and prefers small prey. For the time being, unlike today's snakes, it does not yet have sufficient skull mobility to gobble up larger prey. But it won't be long now. In a few million years' time, Titanoboa will be one of the most ferocious predators of its time. In the Cretaceous, while Titanoboa was not yet rampant, other large predators were prowling the land, sea and air. They were omnipresent. It's time to go and find them, if you're adventurous enough. They're not nearly as charming as the cuddly cat who loves the living room sofa so much, but they're well worth the trip. Dinosaurs, like plants, evolved considerably during the Cretaceous period. They underwent numerous geological and climatic upheavals that forced them to adapt, and thus to migrate and evolve. Let's take a look at some of these new features in the almost dominant Cretaceous species, the dinosaurs. From the Triassic onwards, but especially in the Jurassic, dinosaurs took full advantage of their environment. This is still the case in the Cretaceous, where they continue their evolutionary radiation and have largely conquered the whole planet. Remember, in the previous period, we saw some very large specimens. Fully happy on the plains, they have continued to diversify and enrich their group. Specimens such as Ampulosaurus, Amargasaurus, and the famous Titanosauriforms appeared. The latter include Argentinosaurus, found in South America, and Paralatitan in Egypt. Titanosaurs are among the heaviest creatures ever to walk the Earth. Argentinosaurs, according to the latest estimates, could reach 8 meters or 25 feet in height, 35 meters or 115 feet in length, and weigh almost 80 tons. Its tibia alone measures over 1.55 meters or 5 feet long. It rubs shoulders with another giant in the region, the Patagotitan, discovered more recently in 2014. It boasts the same exceptional physical proportions. On the African continent in Egypt, Paralatitan is no match for the grandeur of its American contemporaries. Estimates, as with many prehistoric animals, are regularly revised in the light of new comparisons, further fossil studies using today's technology, and new discoveries. In 2006, Kenneth Carpenter, a paleontologist at the Denver Museum in the USA, based a comparative study on another titanosaur Saltosaurus. According to his estimates, our Egyptian specimen would be around 40 meters or 130 feet long, 7 meters or 23 feet high, and weigh close to 60 tons. Other parts of the world have also seen this kind of large size. In 2021, a team identified a dinosaur that was named Australotitan cooperensis. It is thought to be just over 6 meters tall, and its length is estimated at 30 meters or 100 feet. A beautiful baby, don't you think? But what happened to the big sauropods we met in the Jurassic? The animals we just mentioned will gradually replace them. Diplodocus and Brachiosaurus didn't make it to the Cretaceous. Other giants will fill their ecological niche. Energy requirements are high because of their size, and because of their diet, they have to eat a lot to meet their needs. So they're not picky eaters, feeding on a wide variety of plants. Cycads, conifers, palms, grasses, and even the ancestors of rice and bamboo are all part of their menu. They are also thought to have lived in herds. This is confirmed by the presence of nesting sites. Several holes were dug by the females to lay around 20 eggs before covering them with vegetation and earth. Their size was a potential hindrance to predators, but the most powerful and aggressive would stop at nothing. Take Abelisaurus, for example. To defend themselves, they had to live in groups. To increase their chances of survival, these giants also had skin covered with a kind of armor made of tiny scales. Let's move on from these herbivorous mastodons to discover another highly diversified Cretaceous group, the ceratopsians. Marginocephalans are a group of animals that appeared in the Jurassic period. During this period, these animals were often bipedal. In the Cretaceous, however, they evolved to adapt to their environment, moving increasingly from bipedalism to quadrupedalism. At the same time, a new genus of ceratopsians appeared. They moved on 4 legs and are more massive. They gave rise to numerous species and diversified greatly, especially in the Upper Cretaceous. These are the Neoceratopsians. One of them is well known to the general public and is undoubtedly one of the youngest dinosaurs. We're talking, of course, about the Triceratops. At 10 meters or 30 feet long, almost 4 meters or 13 feet high, and averaging 7 to 8 tons, the Triceratops is a very large herbivore that knows how to defend itself. Its head, which alone accounts for almost a third of its length, is quite impressive. Thanks to the large horn protruding from its snout above the nostrils, but also to the pair of horns located just above the eyes, it tries to intimidate predators who might have the audacity to attempt an attack. Unlike other ceratopsian specimens, the Triceratops has a very strong ruff that can also help it in combat. According to recent studies, the ruff and 3 horns may also have served another purpose. One hypothesis put forward by certain scientists is that these assets could also have served as an identity card between congeners, if you like. A process of identification was established to court or dominate another male. This theory is further supported by the later appearance of holes in the skull collar of Torosaurus, a species that was once thought to be separate from Triceratops, and which in the end was probably the adult form of Triceratops. An additional asset for courtship. To get around, this mastodon needed to be well supported on all 4 legs. It therefore has strong, powerful limbs. Its legs are also equipped with hands, with 3 fingers for the front legs and 4 for the hind legs. It walks on tiptoe with toes extended by hoof-like appendages. Some hypotheses also suggest that Triceratops is a social animal, living in herds or even with other large herbivores. But very few studies have been carried out on this subject. Fossil sites do not allow us to confirm or refute this hypothesis. While some specimens were undoubtedly feathered in the Jurassic, this characteristic is even more prevalent in the Cretaceous. This can be seen, for example, in a small dinosaur specimen compared to the Colossus we've just left. It measures 80 centimeters or 31 inches long and weighs just over 1 kilo or 2.2 pounds. This is the Microraptor. Fossil remains prove the presence of feathers all over its body, including its legs and long tail. In 2012, American and Chinese researchers succeeded in taking their investigations a step further. Microraptor's feathers were black, elongated and arranged in lamellae, but that's not all. This arrangement indicates iridescence, i.e., the ability to change color according to viewing angles or light. Shortly before, in 2011, in Canada this time, fragments of feathers, but also of hair, were found in amber. Feathers perform different functions in our dinosaurs. For some animals, this adaptation enabled them to withstand the long, harsh winters that can be severe in certain regions. This new physical attraction helps them to preserve and maintain their body heat, thus combating the harshness of the cold. For others, they are also used for flying. This is not the case for the vast majority of feathered dinosaurs. We speak more of gliding than flying. Over the course of evolution, however, things changed, and some species managed to flap their wings. Semicotopteryx, on the other hand, is one of the flightless dinosaurs. Nevertheless, it has found the perfect use for its feathers. It has a pygostyle, a bone in the rump of a bird that results from the fusion of the last caudal vertebrae. This little detail is particularly important in this pretty male specimen. In fact, thanks to this pygostyle and its branched feathers, he can produce movements with his appendage and thus attract the attention of females. Here we are again in the midst of lush vegetation in the heart of the equatorial forests. The plants benefit from the heat, but also from the heavy humidity. It's a godsend for these plants. Plenty of sun and light, always mild temperatures, and never short of water. Creepers, small shrubs, ferns, and flowering plants take full advantage of this paradise-like territory. You'd think you were in the middle of the Amazon rainforest, but there's no chance of encountering the animal just a few meters away. It's an ankylosaurus. It's well known to the general public, and children are particularly fond of this dinosaur. It's his club tail that has made him famous. It's made up of bony plates. It's very heavy, as you can imagine. The animal measures almost 10 meters or 33 feet and weighs around 4 tons. His club is of course proportional to the rest of his body morphology and alone weighs at least 50 kilograms or 110 pounds. Is the legend that he uses it to defend himself true? This claim should be taken with a grain of salt. but there's every reason to believe that he used it as a defensive weapon. He transmits his strength to the tip of his tail and uses it as a club. Terribly effective, it's capable of breaking bones. Few opponents dare touch it. And if you look closely at the animal, that's far from its only asset. He's also equipped with a fine suit of armor. This time, it's not for offensive purposes, but to protect him from injury. Like his tail, the armor covering his body is made up of bony plates, dermal plates known as osteoderms. It also has thick scales and large horns at the top of its skull. Given all this defensive armada, it seems quite unassailable. He is surrounded by an impenetrable, unbreakable carapace. No fang could break through it. Yet there is a weak spot. It's the belly. On this part of the body, it has no protection and is therefore very vulnerable. According to scientists, if we compare it with current animal modes of operation and known defensive strategies, this large animal may crouch to the ground to protect this part of its body during an attack. As soon as it has the opportunity, it propels its club against the attacker, trying to be effective with the first blow. This particularity has come in handy when it comes to surviving in hostile environments, surrounded by large carnivores, each more ferocious than the last. Nature has enabled them to evolve and adapt, not only to their predators, but also to their environment. Our first dinosaur on this list lives in the USA. It's the famous T-Rex. The Tyrannosaurus rex is undoubtedly the king of the dinosaurs, and the most popular of them all. Although known since the 1900s, it continues to reveal new facets of its personality through new studies and analysis tools. The most terrifying and legendary predator of the Cretaceous still has plenty to surprise us. Let's start by answering one of the biggest questions about him. Why did he have such small arms? When you consider its imposing size, 13 meters or 43 feet long, almost 4 meters or 13 feet high, and around 10 tons of muscle, arms measuring just 70 centimeters or 28 inches seem rather ridiculous, don't they? And yet, nature is well done, and these had their uses. At first, researchers thought his arms were probably in the process of regression. They were of no use and in short doomed to disappear. But later research revealed that the arm bones had bony ridges that allowed muscles to be inserted. This time, the front legs were seen from a new angle. It finally appears that T-Rex may have used its small arms to balance its body and to dart off to chase prey. He wasn't the king of sprinting. Others were much faster. But capable of moving at 20 kilometers per hour or 12 miles per hour, he achieved his goals with relative ease. Another very surprising fact was revealed in 2014 by Canadian paleontologists. According to their studies, contrary to what you might think, this carnivore may not have lived alone, but in a group. Footprints show that these animals move parallel to one another. Is this an isolated case or a general one for tyrannosaurs? Research is continuing on this subject. Finally, the T-Rex was not a cold-blooded animal, but a warm-blooded one. Its body temperature must have been between 35 and 38 degrees Celsius, or around 95 and 100 degrees Fahrenheit. Unfortunately for the surrounding prey, their metabolism was very energy-hungry. It therefore had to eat a lot of meat to meet its vital needs. Speaking of meals, what did Tyrannosaurus rex eat? He wasn't a picky eater, attacking all kinds of dinosaurs, even if they were mainly ornithischians, herbivores for the most part. On the menu are ceratopsians, such as Triceratops, as well as Parasaurolophus and hadrosaurs. Let's leave the USA and head for another continent, Africa. Now the land of lions, it was once known as the land of Spinosaurus in the Cretaceous period. The Spinosaurus is one of the continent's great predators. Despite the lack of information about them, we do know that they were formidable hunters in their day. Spinosaurs have adapted to their environment, but also to the prey available. They can be piscivorous as well as preying on juvenile dinosaurs and pterosaurs. Armed with sharp teeth and quite active, they don't back down easily when faced with potential prey. How did it hunt? What position did it adopt to move or attack? The answers are still rather vague. Before 2014, posture was the subject of debate, for want of evidence to support one theory over another. Then, with the discovery of the hind limbs, the puzzle was put back together and new hypotheses developed. According to these elements, the quadrupedal posture is favored. The forelimbs were relatively short compared to the others, signifying a forward center of gravity. As for its environment, scientists believe that it was, like crocodiles for example, a semi-aquatic animal. But nothing has yet been proven, and research on the subject continues. Let's take a look at a European predator. This is the Archovenator, a member of the genus Abelosauridae. There's little doubt that it was bipedal. It had a large skull with short, sharp teeth. Its diet, on the other hand, raises more questions. It was undoubtedly a carnivore, but it could also have been a scavenger. His small arms and the 4 fingers of his hands, which enabled him to extract the viscera from dead animals, reinforce this theory. But it also had a powerful neck, which this time favors the predatory hypothesis. It could then have repeatedly bitten and weakened its prey until they succumbed or abandoned themselves to their sad fate. In Europe, as we saw at the start of our Cretaceous journey, the climate was very different from the one we know today in this region. The tropical climate offered lush, rich, and diverse vegetation, an ecological niche that favored the expansion of species such as titanosaurs, like Astingonosaurus, but also Rhabdontidae, like Rhabdodon, and Nodosauridae, like Struthiosaurus. They fed on ferns, ginkgos, and chaeries. While these vegetarians and carnivores found everything they needed to feed and reproduce, others were unable to adapt to their new living conditions. The great diversity of dinosaur species doesn't mean that everything was easy for them. Indeed, for some adaptation was difficult, and for others impossible. Some species, despite being very well established during the previous period, eventually became extinct. This was the case, for example, of the Stegosaurus and the Allosaurus, 2 major Jurassic predators. A large number of species are renewed by the disappearance of other animals that were unable to adapt. All diets and environments are affected by these radiations and disappearances. Dinosaurs, although dominant during the period, did not all make it through the Cretaceous with equal ease. Another group of animals, sharing the territory with the dinosaurs, also faced obstacles to survival in this dangerous and hostile zone, filled with the most terrible carnivores the Earth has ever known. Despite everything, they managed to survive. These are the mammals. Nothing was won for them, and yet their group, of which we are a part, is still present on Earth today. Contrary to what we have long believed, mammals did not conquer the Earth once the dinosaurs had disappeared. Up until around 2000, the scarcity of fossil remains suggested that dinosaurs were omnipresent on Earth and undisputed masters of the land. Mammals, on the other hand, would have taken full advantage of their disappearance to finally establish themselves and dominate the world. In reality, however, things didn't quite work out that way. Despite their small size, they had prepared their weapons, if you can put it that way, long before the dinosaurs disappeared. These were effective enough for them to survive. One thing is certain: dinosaurs are numerous and widely present on Earth. But they weren't the only occupants of the planet at the time. Mammals have already established themselves on our planet. Unlike the dinosaurs, mammals are still very much present today and have conquered every environment: land, sea, air, forests, deserts, mountains. In short, they're absolutely everywhere. There are almost 6,500 different species on Earth today, in all environments. They didn't make much of an appearance at first, but it's quite an achievement to have made it this far when you consider what they had to go through. A great story for these animals. And yet, nothing could have foreshadowed such a bright future. Do you think you had even the slightest chance of surviving alongside the colossuses we met earlier? So how did the mammals manage it? Incredible as it may seem, it was their small size that was their first advantage, but also their way of life. In the midst of the fearsome T-Rexes and other giant carnivores, our mammals have indeed succeeded in imposing themselves, but not by becoming terrible predators. To live happily, let's live hidden, as the saying goes. And mammals followed this valuable advice throughout the Mesozoic. Fossils dating back to different eras of the Mesozoic bear witness to their presence. Adelobacillus was already on our planet alongside the first dinosaurs in the Upper Triassic, for example. Laulestes was also found in the Jurassic, but they're far from the only ones. We could also mention Haramaiada, as well as Kisho, Ambondro, Trecnotheria, and Scheutheridae. More discreet than dinosaurs due to their much smaller size, mammals were still very present in the Cretaceous. Since the Triassic, they have diversified considerably and are increasingly numerous in a wide variety of forms and environments. Almost all diets can be observed, from vegetarians to insectivores. Far less frightening and seemingly less aggressive at first glance, they are no less dangerous for all that. At least for some of them. Rapenomamus robustus, for example, is quite similar in size to the opossum, but its courage is far from proportionate to its size. It doesn't hesitate to munch dinosaurs if necessary for its own survival. Indeed, the remains of a Psittacosaurus, a herbivorous dinosaur, have already been found in the stomach of a 130 million-year-old fossil specimen. Not all mammals were affected by this diet and this particularity, but it's important to know that these species could also prey on certain members of the dinosaur dynasty. Mammals are characterized not only by their fur, but also by their ability to generate their own heat. This is an extraordinary evolution for the living world. These animals don't need to capture the sun's rays to store heat. The other thing that all mammals of this era have in common is their very modest size, almost all of them around 10 centimeters at most. They resemble small mice or shrews. This flaw, or weakness if you like, is actually an asset, as it allows them to slip more easily into their environment. Between the dinosaurs that largely occupy the plains, the pterosaurs that have invaded the skies, and the marine reptiles that have conquered all the world's waters, it's hard to get around in such a hostile and dangerous environment. Unless you're small and fast. Thanks to this morphology, they are almost invisible, so they are hardly noticed by the giant carnivores they live alongside. But that's not their only particularity. The vast majority of them are also nocturnal animals, and that changes a lot too. While large predators move about during the day, small mammals hide in small shelters. In the earth, but also in the surrounding vegetation, digging burrows and galleries. Protected from predators, they can stay this way for hours without being seen or caught. When night falls, mammals can emerge without risking their own survival. The expression, "when the cat's away, the mice will play," takes on its full meaning here. Our first mouse-like land mammals take advantage of the sleep of large predators to go in search of food, with a light heart and a serene mind. They generally feed on insects of all kinds. Once their bellies are full, they quickly find their shelters. They'll wait for the sun to set once more, and come out under a beautiful starry night. But to hunt so well at night, our Cretaceous mammals have evolved new abilities. Yes, living at night isn't for everyone. They have something that many Cretaceous animals don't: highly developed hearing. While most animals can only rely on their eyesight in the dark, mammals can have total confidence in their ears. This hearing has evolved thanks to the appearance of tiny bones in the ear. They are quite difficult to see on such small fossil skeletons, but they are nevertheless very important and mark a real turning point in the evolution and different radiations of mammals. Different types of mammals can be observed in the Cretaceous. The Harameidas, for example, which appeared as early as the Triassic and are still present in the Cretaceous, are a clade of squirrel-like animals with a long cat-like tail. They have not yet evolved to the point where they can hear and live at night. However, they manage to survive thanks to their arboreal lifestyle. They feed on plants, but also on fruit, seeds, and even insects. In case of danger, some members of this clade, such as Arbora harameia, Villovolodon, or Myopatagium, can rely on the skin membranes called patagiums stretched between their limbs. These enable them to glide between two trees. We can also mention Zolombolesti, which looks a little like a shrew. Just 20 centimeters long with an elongated snout and well-developed eyes, it had teeth that enabled it to feed on a wide range of insects. Like most of their congeners in the same group, they are small animals, so they don't need very large quantities of food to survive. Again, this may seem an insignificant detail, but it's one of the reasons why they were able to survive easily in the midst of the dinosaurs, and also what will help them overcome the coming crisis. but we'll come back to this in the chapter devoted to the latter in a few minutes' time. Let's take a look at another member of the mammalian family. This is Cronopio-dentiacatus. It belongs to the Dryolestioidea clade. It lives in the Upper Cretaceous and benefits from the evolutions we detailed earlier. First of all, it is small in size, comparable to a modern mouse. It has a slender snout, well-developed round eyes, and long canines for feeding on insects and small invertebrates. It can also hunt small vertebrates like this member of the Lacertilian family, for example, which could very well be our Cronopio's next meal if their paths cross. But what's most noteworthy about him is the evolution of his skeleton, and in particular his skull. In particular, we can see the squamosal bone. This skull bone, found in the temple region, is essential for the temporomandibular joint, which will influence its ability to hunt and feed, but it will also house the hearing organs with a tympanic cavity. And now let's go to the ocean. Under the waves, there have been some significant developments. The marine world promises some wonderful encounters. That's if your heart's in the right place, of course, because the creatures that reside in these marine lands are far from peaceful. Around 140 MA, the climate warms up. Water temperature, logically enough, also benefited from this rise in temperature. Warmer water means an abundance of marine microorganisms, especially plankton. Plankton is a godsend for the marine environment, with all marine organisms benefiting directly or indirectly from this abundance of microorganisms. Life abounds at every level and in every form, from echinoderms such as starfish and sea urchins, to sponges, invertebrates such as corals, crustaceans, and mollusks, right through to fish. Other aquatic animals, notably sea turtles, appeared at 100 million years ago. Like other marine reptiles, they could reach gigantic sizes during the Upper Cretaceous, up to 3 meters or 10 feet long, and 5 meters or 16 feet wingspan for Archelon, for example, which is quite similar to today's leatherback turtles. The two families we know today, Chelonidae and Demochelidae, already existed in the Cretaceous. In fact, these families include the loggerhead or hawksbill turtle and the leatherback turtle, respectively. And of course, there are always fish. All over the globe they abound. Some rays and sharks rival mega-predatory reptiles. Giant sharks, such as Scaponorhynchus, reach lengths of almost 5 meters or 16 feet, while Otudus approaches 6 meters or 20 feet. Around 100 million years ago, giants such as Ledsictus were also observed, reaching lengths of over 15 meters or 50 feet. Yet it feeds on plankton, proving that a carnivorous diet is not necessarily a prerequisite for exceptional size, even at that time. Others of average size are no less formidable carnivores. For example, Encompasses, found in North America and the Mediterranean, really skewers its prey, such as cephalopods and other small fish, thanks to its long saber-shaped teeth. We have already discussed marine reptiles at length in the Triassic and Jurassic periods. During the Cretaceous period, these animals are still very much present. All of them? Not quite. Remember, we talked about the fragility and decline of some of them in the Jurassic period in particular. The Cretaceous period brought their demise. Do you remember which marine species we're talking about? It's the ichthyosaurs. Although scientists have put forward a few hypotheses about their disappearance, it's still difficult to formulate any real answers. Ichthyosaurs may not have made it this far, but others are making the most of their environment. Plesiosaurs are rampant. But mosasaurids are also becoming the new terrors of the seas. Plesiosaurs are animals characterized by a massive body, 4 identically sized swimming fins, and above all a huge neck, extended by a small head. In a way, they're a cross between a snake and a turtle, but XXL in size. The all-time champion in terms of neck length is undoubtedly Elasmosaurus. It has between 70 and 72 vertebrae, depending on the scientific source. Either way, it's a record. Its long neck represents almost 2/3 of its total length. It is estimated to be around 10 meters or 33 feet long, with a neck length of 7 meters or 23 feet. The male just in front of us is, like his congeners, perfectly adapted to aquatic life, despite his imposing size. He's long and definitely heavy, between 2 and 9 tons, and he has a streamlined body and powerful swimming legs. It is a very good swimmer and quite active. If it didn't swim fast, it could swim for a long time. During the late Cretaceous, the American West and part of today's Midwest were covered by a shallow expanse of sea. It was in this region, present-day Kansas, that the very first fossil of this dinosaur species was found by Edward Drinker Cope in the 1860s. Since then, a great deal of investigation and research has been carried out on this very special dinosaur. Although it was aquatic, like some of our marine mammals, Elasmosaurus breathed air at the surface. He was not equipped with gills but with lungs. So, depending on his estimated lung capacity, he would ascend perhaps every 10 to 20 minutes to take a deep breath of air. Legend has it that this dinosaur is the Scottish Loch Ness Monster. Plesiosaurs are very diverse, including Hydrotherosaurus, which fishes with its 6-meter or 20-foot long neck. But there are also members of the mosasaur group in the vast ocean. Tylosaurus will be the mosasaur effigy of our Cretaceous journey. Tylosaurus is a marine reptile that is actually quite similar to a monitor or snake. It dominates shallow waters and was one of the dominant predators of the period. It is very imposing and can reach 12 meters or 40 feet in length. Its skull alone measures over 1 meter or 3 feet. A ferocious predator, it was also very aggressive with its direct competitors. Paleontologists have found traces of lesions, notably on the snout bones, which suggest quite violent battles with other large predators. In the remains of Tylosaurus stomachs, scientists were able to observe how dangerous and powerful they were, attacking all kinds of prey. These included Elasmosaurus, our great plesiosaur, as well as sea turtles, sharks, other mosasaurs, and seabirds like Hesperornis. In short, nothing really stood up to him. If he had to get his head out of the water for a fraction of a second to tackle a pteranodon in the middle of a fishing trip, he wouldn't hesitate for a moment, and he'd make mincemeat of it. This unfortunate pteranodon will serve as our transition to the conquest of the Cretaceous sky. Let's take a look at how these flying reptiles managed to serve over the period and how they evolved. Some of these sky gods, the flying reptiles, continue to evolve. Indeed, they were still widely present in the Cretaceous period. But competition, even in the air, is fierce. Some species, notably those that appeared in the Triassic, are slowly declining. This is the law of nature. Not all species manage to adapt sufficiently to retain their place in their ecosystem. The first birds did appear, and to say the least, they adapted to their ecological niche and to specific climatic and geological conditions. As proof, they are still with us today. Small pterosaurs are gradually giving way to these famous birds. Others, the largest specimens of pterosaurs, are taking full advantage of their extraordinary capacity and have less direct competition. Yes, these giants of the sky are rarely insectivores. They grow to exceptional sizes and prey on prey that matches their physical capabilities. Quetzalcoatlus is without doubt the largest pterosaur of all time, at least according to our current knowledge. Imagine 3 cars lined up lengthwise, or a bus with 4 axles. The latter could fit between the 2 wingtips of this giant reptile. It's almost unimaginable to think that an animal with such a wingspan, 16 meters or 53 feet wide, could fly, yet it was indeed the case. On the ground it walked on all 4 feet. Footprints confirm this. As for flight, it turns out that it could take off from the ground with a jump, then operate a beaten flight, i.e. with repeated flapping of the wings. Scientists still have some doubts about its diet. The fossil remains were found on land, not near the sea. We can therefore rule out the piscivorous theory. Perhaps it was a scavenger? Unless it captured freshwater prey or small vertebrates. Others believe that the combination is also possible with a mixed diet of prey and carcasses. Let's take advantage of the discovery of these flying reptiles to evoke another member of the great family of sky gods, the first dino bird. Archaeopteryx is an avian dinosaur and one of the very first to be discovered. A feathered dinosaur with a bird-like appearance. We can already see in this specimen elements comparable to our present-day birds, such as the proportion of wings. However, it is not clearly attributed with the origin of birds. Research on this subject is ongoing, and the elements in our possession do not allow paleobiologists to determine exactly whether this is one of the first direct ancestors. Generally speaking, there are many areas in which Archaeopteryx is the subject of scientific debate. How it flew, for example, or how it took off is still very unclear. We know very little about its way of life. Some agree, however, on the possibility that it lived in trees and fed on insects. Its muscular strength is indeed quite weak compared to our birds. Living in an archipelago of islands in the tropical seas, it may also have fed on fish carcasses or worms. Nothing is less certain. In the category of avian dinosaurs, we can also mention other, more or less well-known specimens, such as Iberomysornis romerali discovered in Spain, or Confuciusornis. The latter was modest in size, measuring around 50 centimeters or 20 inches, and weighed no more than 1.5 kilograms. It's a rather paradoxical specimen. It is both a little more evolved than Archaeopteryx in some respects, and considered more primitive in others. On its skeleton, for example, we can observe the pygostyle, the famous fusion between several caudal vertebrae and a sternum. These elements are essential for the attachment of muscles useful during flight. Another peculiarity is that it also has a large cartilage that could have attached the pectoral muscles. On the other hand, it retains large claws on its front limbs, and its skull is less developed and more primitive than Archaeopteryx. Unfortunately, most of the animals we have encountered so far, apart from mammals and certain avian dinosaurs in particular, will disappear within the next few thousand years. The Upper Cretaceous is coming to an end, and a terrible biological crisis is starting to unfold across the world. Although far from being the only extinction event, indeed it's already the fifth in our planet's history, the one that marks the end of the Cretaceous and the beginning of the Paleogene is the most popular of all. It marks the end of a whole section of our planet's history, that of the Mesozoic era. The Cenozoic, our era, will begin on the ashes of the previous era. Like all extinctions, it is still very difficult to establish their origins, millions of years after the events took place. As our knowledge evolves, but also as new discoveries are made, hypotheses are sometimes confirmed, sometimes refuted. Added to this temporal break are multiple causes. We sometimes imagine that such a catastrophe is sudden, rapid, and the result of a single event. On the contrary, the causes are often multiple and extend over a very long period of time, sometimes thousands of years. In the case of the Cretaceous, there have been many hypotheses, and these have been the subject of much debate. Nevertheless, as paleontological, archaeological, biological, and even geological investigations and studies have progressed, many elements converge towards some of these hypotheses. Perhaps because, despite the millions of years that separate us, this crisis remains the closest to our current period, the vestiges of this event can still be observed in the four corners of the world. A volcanic eruption has irreparable consequences. 65 million years ago, in India's Deccan Traps, several volcanoes erupted. The problem was that this eruption lasted a very long time. It lasted between 300,000 and 1 million years. Thick smoke then penetrated the atmosphere, causing acid rain. But this is not the only plausible cause, according to scientists. During the same period, scientists also suggested the impact of an asteroid the size of Mount Everest. In one of the Earth's geological layers, 65 million years old, iridium was found, which tends to prove the impact thesis. Iridium is a very rare material on Earth, but it is widely present in the universe, notably in certain metallic asteroids. We also know that at the same time an impact took place in Mexico, at Chicxulub. The impact crater measures 180 kilometers in diameter. Plunged into darkness, battered by dust, gas, and acid rain, the living world suffocated. First, the blast. It's immeasurable. Fauna and flora are swept from the surface for hundreds of kilometers around the point of impact. As a domino effect, earthquakes, tsunamis, and incandescent debris are propelled into the atmosphere. From then on, there's no stopping the biological catastrophe that's about to unfold. Thousands of tons of this incandescent debris, dumped into the atmosphere, fall back onto the ground of our blue planet, which literally bursts into flames. Fires start everywhere. Millions of hectares of vegetation perish under the flames, as do many animals that are unable to escape such a blaze. You'd think that was the end of it, but it doesn't. As we said earlier, a crisis lasts for a long time. While the consequences for flora and fauna are already catastrophic, nothing is over yet. On the contrary, this is only the beginning. Dust accumulates in the atmosphere, preventing light from reaching the ground. Plants, deprived of their beneficent sun, can no longer use photosynthesis as a source of energy. Unable to adapt to such conditions, much vegetation disappears. The gases released into the atmosphere as a result of the impact and the various eruptions will lead to acid rain. The first to be affected are plants. But soon, large herbivores are also affected by this new catastrophe. Our travels have shown us time and again how important every link in the chain is. The large herbivores take their toll on the carnivores, who can no longer find enough food to eat. It's a veritable hecatomb. While some animals become scavengers and were able for a time to feed on all the unfortunates who perished as a direct result of these catastrophes, nutritive resources soon ran out again. Death once again befalls the last survivors. In the ocean, marine animals are no more spared than those living on land or in the sky. Acid rain, of course, affects all the world's waters, as does ash fallout. The more fragile plankton is soon in trouble, and at the same time, so are the many species that depend on it. Vegetarians and carnivores alike are gradually sinking. Thousands of species, whether on land, at sea, or in the sky, will succumb over the millennia to this massive catastrophe. They find themselves powerless in the face of these new climatic and geological conditions. The food chain is completely broken. Unable to feed and drink to meet their vital needs, they perish one by one. One group, however, manages to survive despite all the disastrous consequences of this unprecedented crisis. Probably guessed it, the mammals. Of course, some of them will also disappear, but a few will manage to survive. As we have seen, small mammals are able to live at night. This permanent lack of light is therefore not a problem for them. They can orientate themselves and move around despite the lack of light. The sun brings light, but also heat. In addition to darkness, which can make life on Earth impossible for many species, cold is also very difficult to overcome. But mammals are animals capable of generating and maintaining their own heat. Once again, these skills enable them to fight for survival. Their small size and modest need for food also enable them to sustain themselves with greater ease than large animals, which require astronomical quantities of plants or meat to meet their energy requirements. While the Mesozoic is often referred to as the age of the dinosaur, the Cenozoic is known as the age of the mammal. Only crocodiles, turtles, lizards, and snakes, and certain families of mammals and birds survived the crisis. Mammals will then become a very important species in this new era that is taking shape. But that's another story, another journey.